In this lecture, we'll see undirected graphical models. These are the things which we are going to see. What is the need of undirected graphical models? And what do you mean by conditional independence in undirected graphical models? Next, we'll have a comparison of directed and undirected graphical models. And in the next lecture, we'll be discussing about the parameterization and examples of undirected graphical models, or it's also called Markov random fields. So here what you see in the top is a directed graph, and on the bottom is an undirected version of the directed graph. So how this undirected graph is generated from the directed graph? What is the process? It's done by moralizing the directed graph. Moralization means, for example, take node 7. You can see that node 7 has got three parents, 4, 5 and 6. 4, 5 and 6 are the parents of 7. So in moralizing, basically what we do is we link them. Similarly, node 5 has two parents, 2 and 3. We marry them. So when we moralize, we can see that whatever the conditional independence relation what was there in the directed graph, that may not be maintained in the undirected version. So why do we actually need undirected graphical models? This is an easiest example. Let's think about random variables in a graph constructed out of pixels of an image. Let's say this is an image, and x1, x2, x3 are the pixels of an image. So we constructed a graph out of these random variables which are pixels in an image. It does not make sense to actually put directions in case of pixels of an image, because there is no notion of directions in an image, right? So something like this, that is something like this pixel is a parent of the other pixel, one pixel is a co-parent of another pixel, and so on. So that sort of relationship will not be available in case of an image, right? That doesn't mean anything, right? So in image analysis and in spatial statistics, we require something known as undirected models. Let's see this example to indicate the difference between directed and undirected graphical models. Let's say this is an image with pixel values x1, x2, x3, etc. And let's look at the pixel x8. And in this example, we have put directions to just put directions to say that this is a directed graph, and in this we have removed the direction, and this is the undirected graph. So let's look at x8. Can you tell me in the context of x8, the surrounding nodes of x8 except x2 and x11, what are they? Except these two, x2 and x14, right? x2 and x14. What is this pixels? They form the Markov blanket, right? So the Markov blanket includes the parents. It also includes its children, and what is x12 and x4? They are the co-parents, right? So it includes parents, children, and co-parents. So the idea of a Markov blanket is that if you know the values of the Markov blanket, then that particular node is conditionally independent of anything else in the graph. So in this case, x8 is independent of all the other pixels if you know this x3, x4, x7, x9, x12, and x13, because that forms the Markov blanket. So let's look at the undirected version now. Can once again consider x8. Here the Markov blanket consists of only four nodes: x3, x7, x9, and x13, which are nothing but the neighbors of x8. Because the conditional independence of the undirected graph is defined by the neighbors of a node. If you know the values of these four nodes, then all the other x8 is independent of all the other nodes in the graph. So that's the conditional independence in case of undirected model. So it seems the conditional independence relation in case of undirected graph is simpler compared to directed, because if you think of d separation to go from x8 to any other nodes, we have to go through any of its neighbors. So that itself is the Markov blanket. So point is that the conditional independence relation in the context of undirected graph are very simpler compared to the that of directed graph. Now let's see the advantages and disadvantages of undirected graphical models. The undirected graphs are symmetric. There is no notion of parents, children, co-parents, etc. So everything around the node is symmetric, and therefore they are more natural for certain domains such as spatial data, image data, etc., or some of the relational data. Another advantage is that the discriminative directed undirected graphical models, which we'll see later, something known as conditional random fields. It is better than the discriminative directed graphical models. However, there are some disadvantages also. The parameterization of the joint probability distribution in an undirected graphical model is in terms of clicks. So there is no physical meaning there. So they are not going to make probabilities. So they are less interpretable compared to directed graphical models. And the parameter estimation is very complex and computationally more expensive also. Now let's see the conditional independent properties of undirected graphical models. In an undirected graphical model, the conditional independence relation is very simple compared to directed graphical models. It's simple graph separation. For example, let's say we have a graph like this, and in which we have three different sets of nodes. Let's say this set of nodes 1, 2, 3 into 1, and this is another set of node, and this is another set of nodes, something like that. So let's say you have three sets of nodes A, B, and C. So XA is the set of nodes, XB is the another set of node, and XC is the other set of nodes. And let's say that XA is independent of XB given XC. XA is independent of XB given XC. That is, C separates A from B. This is what we call a global Markov property. So if you have three sets of nodes, and the first set of node is conditionally independent on the second set of nodes, given the third set, means that it is the global Markov property. In the example below, if you look at the nodes 1, 2, and 6, 7, they are conditionally independent given 3, 4, 5, because all the paths from 1 to 2, 1 or 2 to 6 or 7 must pass through 3 or 4 or 5. So that's the global Markov property. Next is local Markov property. The local Markov property is basically defined in terms of immediate neighbors of a node. So if you fix the immediate neighbors of the immediate neighbors as the Markov blanket, so if you fix the immediate neighbors as the Markov blanket, then this node will become separated from all the other nodes in the graphs, and this is called the local Markov property. In this case, x8 is if you fix the blanket x3, x7, x9, and x13, then x8 will be independent of all the other nodes. So that is local Markov property. So here is an example. Given 2 and 3, one is independent of all the other nodes in the graph. So all the paths from 1 to any other nodes is going through 2 and 3. Next is pairwise Markov property. Two nodes are conditionally independent if there is no direct edge between them. For example, uh, in this case, x8 and x9 are not conditionally independent since there is a direct edge connecting both. X7 and X13 are independent given all the other nodes because there is no direct edge. Means that X7 and X13 are conditionally independent given all the other nodes. So that implies the pairwise Markov property. An undirected alternative to D-separation. We have seen in the beginning that the conditional independence relations will not be maintained if you moralize a directed graph, right? And while constructing an undirected version, we do moralization itself. So let's look at this simple example A, B, C, which is if you moralize, you get this undirected graph A, B, C, and you can see that the in this example, with the D separation, if you fix B, there is no path from A to C. So given B, A, and C are independent, but in the directed version, A and C become conditionally independent, right? That is, if you don't know B, then A and C are. If you don't know B, then only A and C are independent. So immediately you can see that the conditional independence relations are not the same between a directed and undirected graphical models. So with moralization, which is not going to maintain the conditional independence properties of a directed graph. So this is the moralization thing which we have done in this graph. So the unmarried parents are linked together. That is how we moralize. So as a solution to this, what let's see this directed graph and the corresponding moralized undirected graph. Given two, in this case, given 2, 4, and 5 are conditionally independent, but in the moralized undirected version, given 2, 4, and 5 are not conditionally independent. We can actually fix this and make this sort of this graph captures a similar conditional independence as that of directed graph by constructing something known as ancestral graph. Given 2, 4, and 5 are not independent. Can you tell me why this has happened in this graph? Which link is actually creating a problem? or which edge is responsible for destroying this relation, that is 4 independent of 5 given 2. This 4 and 5 are link. This 4 to 5 link. So this 4 to 5 link was created. Why? Because of this common child. So you observe that this link is actually not needed till we consider 7 or any of the descendants of 7, right? So for that, what we do is, if you want to prove the conditional independence, say A in independence of B, given C, then you form what we call as the ancestral graph. So start with a directed graph which contains only A, B, and C, nothing else. In the previous graph, you can just remove from the previous graph you can just remove 6 and 7. That is not required now. And we moralize the ancestral graph. We just remove 6 and 7. So what we get is we get this graph, and then we do moralization. Now we can see that the conditional independent relations of the previous graph is followed in the. So basically what we do is we construct the ancestral graph, and the ancestral graph is moralized, and we construct the undirected graph. So that will be the best method for maintaining the conditional independence relation as that of the directed graph. This is the relation for a graph being an IMAP of a distribution. So the relation implied by the graph are the subset of the independent relation implied by the distribution. So this is the relations in the graph, and this is the probability distribution. Now define G to be a perfect map if then the independent relations are the same. In the independent relations of the graph and the independent relations of the distribution are the same, then we can say that this is a perfect map. Directed models and undirected models are perfect map for different sets of distributions. So in this sense, we cannot say which one is more powerful. Now, let's see an example. Let's consider the undirected graph. Can you give some independence relations on this graph? Let's see this example, and some of the independence relations in the graph. A is conditionally independent of C, right? A is conditionally independent of C given what? Given B and D, right? Similarly, B is conditionally independent of D given A and C, right? Right. So the valid question is that is there a directed graph that encodes the same relation as that of the undirected conditional independence? So we have a undirected graph here and two conditional independence relation. Can you construct a directed graph which encodes the same conditional independence relation as that of? So is it possible to construct a directed graph which encodes the same set of independence relation as that of the undirected graph? Here the answer is no, because you can try as many as examples. Here there are given two examples. In the first case, A and C are independent of B and D. That conditional independent relation is valid. But let's look at the other relation given A, B, and D are also independent. In the second example, A and C are conditionally independent of B and D, but B and D are always independent, right? So this is a directed graphical model, and this is undirected graphical model, and there is something known as caudal graph. That is, in that case, the conditional independent relations are the same for directed and undirected graph. So this set is called the caudal graph. So in a caudal graph, if we collapse together all the variables in each maximal click to make mega variables, then the resulting graph will be a tree. So if that relation is valid, then you can see that the conditional independent relations will be the same in case of directed and undirected graphical models.